Okay, let's take a look here at even and odd functions. This is page 7 of the 0.2 Algebra 2 review packet. Although this is a topic that you may not have seen in Algebra 2 before, but it's pretty reasonable to pick up. So first we're going to talk about even functions, okay? And this is a unique definition, and it is defined as a function f of x is equal to f of negative x. Okay, so even functions are defined as f of x is equal to f of negative x. Now, what does that mean? Means whether we put in a positive number, x, or the negative of that same number, x, right? Whether we put in the positive x or a negative version of x, we will get the same result. Okay? This creates what is called a symmetry, or even functions are symmetrical over the y-axis. And it sort of is like a reflection over the y-axis would produce the same function. So if you reflect the function over the y-axis, it looks exactly the same. Okay, so let's take a look at some examples. So let's start with the function f of x is equal to x squared plus 1. And let's look at this first on a graph. So if I graph a set of axes, an or a y-axis and an x-axis, x squared plus 1 looks like a parabola with the vertex just moved up 1 unit, the parabola is shifted up 1. So there you go, and you can look and see that that's pretty symmetrical over the y-axis. If we were to reflect this function over the y-axis, it ought to look exactly the same. If we get a little formal here, and if I say there's some coordinate x that corresponds to some output f of x, and then I have some coordinate negative x, right, the same thing, just in the negative direction. Let me move that over just a hair. Negative x, and we go up, and I have f of negative x. Well, those two are supposed to be the same y-coordinate. So if I go the same distance here, x and negative x, well, my outputs should be at the same y-coordinates. And that's a little fancy of a definition, but it's good to look at. Going back to this idea, whether we put in a positive or a negative version of the number, we'll get the same result. So let's look at that. If I build a table of values, do it in pink, okay? I have x and I have f of x. Starting with 0, I plug in 0, I get 1. If I plug in 1, 1 squared is 1 plus 1 gets me to 2. But if I were to plug in the negative version of 1, negative 1, negative 1 squared is positive 1 plus 1 also is 2. So you'll notice that whether I plug in negative 1 or positive 1, some positive x or the negative of that same number x, and x could originally be the negative, and then negative negative makes positive. But the point is, our outputs are the same. And no matter what number we choose to put in, whether it's 2, 2 squared is 4 plus 1 is 5, negative 2 squared is positive 4, plus 1 is also 5. No matter what I put in, there's this symmetry. So the function is said to be symmetrical over the y-axis. Okay, so that's basically the idea behind even functions. And now we can shift our function up and down. So if I draw another function and I say, let's call it g of x is equal to x squared plus 2. That's still symmetrical over the y-axis, so that would be considered an even function. I could even say something like an absolute value function. So I could say h of x equals 2 times the absolute value of x. and then that would produce a symmetrical function, so that would be considered even. It could be positive, it could be negative, maybe it's j of x equals negative absolute value of x minus 2, so that'd be something down here. And you can even get really cool functions too, and we'll learn about these later. But let's say we had k of x is equal to the cosine of x. And don't worry, you haven't learned that yet, but that's also a symmetrical function. It looks a little different, and I'll try to draw the same on each side. But that would be symmetrical over the y-axis as well. Okay, so how do you test? Okay, let's see. Test if even. And really all you want to do is plug in negative x and see what happens. So if I have, let's say, f of x equals x squared plus 1, our original function, and I go and I try to plug in f of negative x, well, I'm plugging in negative x in place of x, right? So I'm going to say f of x equals negative x squared plus 1. But a negative times a negative is a positive. So negative x squared and positive x squared are the same, equals x squared plus 1 equals f of x. So we'd say even. Okay, it checks out. Let's test another one. If I wanted to test h of x, so h of x, there was 2 absolute value of x. So let me test h of negative x. Well, that's 2, plugging in negative x in place of x. But the absolute value of x and the absolute value of negative x is going to be the same. Regardless of whether it's negative or positive, it's just going to turn it to the x value, the magnitude of x. So this is 2 absolute value of x, which was our original h of x. So h of x equals h of negative x, so we must be even. Okay, and let's look at an example when it doesn't work. So we'll use, we'll try purple. So say I had m of x is equal to a quadratic, x plus 1 squared, and I went to plug in m of negative x, and I would get negative x plus 1 squared. And now, maybe it's obvious that those aren't the same, and maybe it's not, so maybe let's try expanding these and see what happens. So this would be x squared plus 2x plus 1. And if you watched my last video, you'll see that square of a binomial comes up all the time. Super useful to know. This one would be x squared minus 2x plus 1. So though they're pretty similar, they are not the same. So we'd say m of x does not equal m of negative x because of our middle term. In one case, our middle term ends up being positive 2x. The other one, it ends up being negative 2x. So we would say it is not even. And if we look at that on a graph, draw a little graph down here, x plus 1 squared shifts our parabola, our parent function x squared, left 1 unit, so we'd be over here. And you can see, well, that's not symmetrical over the y-axis. Not symmetrical over y-axis. It is it does have symmetry. It is symmetrical over its vertex, or this axis of symmetry at x equals negative 1. There is a symmetry there, but it's not symmetrical over the y-axis, which is our definition of even function. F of x has to be f of negative x. So it sort of fails that test, and we would say it's not even. I'm going to give us one more example. So we'll look at a slightly more complicated one. We'll call it h of x is equal to x to the 4th minus x squared plus 1. So we don't necessarily know by looking at this if it's even or odd, or neither. Usually if it's not even, that doesn't mean it's odd. It probably means neither. But first off, the fact that we have a degree of 4 and 2 and all that means there's a potential for it to be even. If I had something like h of x equals x cubed plus 2x plus 1, this is just no way it's even because our function looks like this. So if our if we were going to reflect it across the axis, the y-axis, wherever it is, we're going to look something like this, and that's just not the same. Like, there's no way. Whereas like a even power function, it maybe looks something like this, and so I maybe can reflect that and it still looks like the same thing. So there's no chance this is even, but this could be even. Just because it's x to the fourth doesn't mean it's even. Just like when we looked at here, just because it was squared doesn't mean it's even. We need to actually test it, but this even is a clue. If the degree is even, then maybe it's even. If the degree of the leading term is odd, there's no chance. Okay. Okay. So let's go ahead and try it. So algebraically, we want to test h of negative x. So plug in negative x every time we have x, negative x to the fourth minus negative x squared plus 1. Well, negative x to the fourth is the same as x to the fourth. Negative times negative times negative times negative is just going to turn it back to positive. So no matter what, we could say that h of negative x will be x to the fourth. Then minus negative x squared is positive, right? Negative times negative is still positive, plus 1. And that was our original function. So we would say that's equal to h of x. Therefore, h of negative x equals h of x. And it is, in fact, even. Okay. And if you're curious, this function on a graph would look a little something like this. So we would have a point here, point here, point here, here, here. And we'd shoot off like this. Okay, so we'd see that symmetry over the y-axis. It is even. But just because this is x to the fourth doesn't mean it's even. You have to test, like, it's possible that the other parts of it, like maybe it would be shifted over here and it wouldn't work. So you do have to test it. And just to even further support this idea, if I had x and I have h of x, we're symmetrical over the y-axis. So if I put in 0 for x, I get out 1. If I put in 1 or if I put in negative 1, I should get the same thing. 1 to the fourth is 1, minus 1 squared is 0, plus 1 is 1. Negative 1 to the fourth is positive 1, minus 1 squared, negative 1 squared is 0, plus 1 is 1. And that's these coordinates right here. We have this 0, 1. Here's our 1, 1. In between, we dipped for a bit. And here's negative 1, 1. And then even to show it one more time, we could do 2. So 2 to the fourth minus 2 squared plus 1 would be 16 minus 4 plus 1, or 13. So somewhere up here is 2, 13. And if I put in negative 2 to the fourth minus negative 2 squared plus 1, again, 16 minus 4 plus 1. So it's all the same. We get negative 2, 13. So there are the ideas of the even function. F of x equals f of negative x. The whole point is, regardless of whether we put in a positive number for x or a negative of that same number for x, we will get the same result, creating a symmetry over the y-axis. And you can see that symmetry in this table of values if you plot it out anyways. So that's even function. Okay, now we're going to take a look at odd functions. So odd functions are defined as negative f of x is going to be equal to f of negative x for some function f of x. Okay, and what this will imply is that reflecting over the x-axis, which is the same as this negative x of f of x is like a reflection over the x-axis, is equivalent to reflecting over the y-axis. Okay, reflecting over the x is equivalent to reflecting over the y, which is kind of what happens with f of negative x. So those two things produce an equivalent result. Now, we would also say that we end up with 180 degrees rotational symmetry. So if you rotate your function 180 degrees about the origin, it will end up mapping back onto itself. And another way of thinking of that is reflecting over the x-axis and then the y-axis maps function to itself. Okay, so an example is going to be really nice here. So let's go for pink, and we'll go down here. So if I have a axis, and I'm just going to use this line here, and let's say I start with the function f of x equals x cubed. Now there is an odd exponent, but an odd exponent by itself does not guarantee an odd function, though it's a decent hint that maybe it's odd. So this function looks a little bit something like this. Okay. And we would say that if we were to take this function and rotate it 180 degrees, it would land right back on itself. So it has that rotational symmetry. Additionally, reflecting over the x or the y-axis, so if I go here, and I would say the graph of negative f of x, a reflection over the x-axis, so that would take my graph and it would make it look something like this, compared to the original graph, which looked something like this, and I'm reflecting all my points over this x-axis, and so that produces the new graph. But that's going to be equivalent to reflecting over the y-axis, f of negative x, because if I put this all together here, and I reflected this function here over the y-axis, right? Oh, actually, let's do it dotted. And I reflect it over the y-axis. So these points go over there, these points go over here. Okay, and I'm going to get this same result. So regardless of whether I reflect it over the x or the y, look at that, I get this same end result. So that's sort of the first definition that I said here. Another way we could look at it is our second definition, is if I start with, say, this function x cubed. Let's go blue. Right? And then I first reflect it over the, let's do it on the same page. So first I reflect it over the y-axis, or it could be the x-axis, and I get to here. So say I reflect it over the y, and then afterwards I go and reflect it over the x. Well, I'm going to end up right back where I started. Okay, so that's another sort of definition here. So you could do two reflections, reflect over x and then y, or vice versa. We have this rotational symmetry where if I rotate 180 degrees, I'm going to get to the same location. Or just a reflection over one axis is the same as just a reflection over the other axis. So graphically, that's what's happening here. Okay, if we then consider, well, what might this look like when applied to a table of values? Let's do it. So we have x, f of x. We're calling that f of x is x cubed. So we start with 0, our origin, and we get 0. 1 cubed is 1, 2 cubed is 8, whatever, 3 cubed is 27, negative 1 cubed is negative 1, negative 2 cubed is negative 8, negative 3, negative 27. And we said that negative f of x and f of negative x are supposed to be the same. So if I had f of x, like f of x equals some output, f of x, right? And if I did f of 2, and that equals 8. some input of 2 gives me an output of 8. Well, if I make the second f of x negative and the first inside negative, so f of negative x equals negative f of x. So f of negative 2 equals negative 8. And we see that that's true. If 2 gives me 8, well, negative 2 gives me negative 8. So that's this sort of odd symmetry. And it's rather important that we have this origin. We need to have the origin here. If we don't go through the origin, we're going to have some problems. So if we scroll down a little bit, let's imagine, and I think we could use another page here again. Great. So say we didn't go through the origin. Say this time we had x cubed plus 1. And we go ahead and graph this. And we would have our point 0, 1. Well, we're going to have a problem because now we don't have the ability to reflect and reflect again. Say I reflect over the y-axis first. So I'm going to end up right here. Okay, so that would be f of negative x, if this was f of x. But then if I were to reflect instead over the x-axis, well, I would end up here. Something like this. And so that's negative f of x. And you'll notice that those are not equal. F of negative x does not equal negative f of x. So this would not be odd. So we can't just sort of shift around up and down in the way we could with even functions. Okay, we must go through the origin 0, 0 to be odd. Now the reason we were allowed to shift up and down with the even function is because you're only reflecting across the y-axis, and so if you're on the y-axis, you're good. But if you're reflecting over the y-axis and the x-axis, well, you have to be on both, and that's only possible at the origin. So that would be that sort of example. Okay, let's look at some examples and test them out. Or let's actually take a peek at some options. So linear function through the origin, such as g of x, even we'll call it 2x, right, is odd, okay? Has that reflectional symmetry, we're good. If we had a function like, well, there's less examples. I mean, all the polynomial ones, so if I had like h of x equals x to the 5th, that would work. That basically is the same as x cubed. Interestingly, cube root works just fine here. So if I go here, I have cube root of x, which is just sort of like this. That should meet all the criteria as well. If I reflect and reflect again, or if I rotate it 180, we'd be happy. And then we have a new type of function that we haven't learned, but you will learn in the near future. So if I call it j of x is sine x, key thing is we go through this origin. Here we are. And then sine x looks a little something like this. Oop. Keeps doing that forever. Right, it'll go on to do that. And it may not be quite as obvious, but if we were to reflect and reflect again, or if we were to rotate 180 degrees, it actually does map right back onto itself. So we got a couple options for functions. And if we want, we can test them out. So if I wanted to test, right, if a function is odd, I would want to see, say I had f of x equals x cubed. I would want to see, does negative f of x equal f of negative x? So negative f of x, if f of x is x cubed, that would just be negative x cubed. And does that equal f of negative x? So that would be negative x cubed. Well, negative x cubed is just negative, and then whatever x cubed is. Negative times negative times negative is just negative, whatever x is. So we do have an odd function, okay? It is odd. Let's look at another example. So if I have g of x equals x cubed minus 8x, negative g of x would be negative all of that, x cubed minus 8x, which would equal just negative x cubed plus 8x. Okay, comparatively, if I wanted to look at g of negative x, I would plug in negative x, cube it, subtract 8 times negative x. Negative x cubed, we said, is the same as negative x cubed, and then minus 8 times negative 8x gives me plus 8. So we do find, in fact, that g of x equals, g of negative x equals negative g of x. Checks out, therefore it is odd. Okay, and let's do an example that doesn't work. So let's try like h of x equals x cubed plus x squared. So h of negative x would equal negative x cubed plus negative x squared. And h of negative x would be negative x cubed. Negative times negative gives me just positive x squared. Comparatively, if I had negative h of x, I would do negative x cubed plus x squared. Negative h of x would be equal to negative x cubed minus x squared. And you'll note that's not the same. Okay, there's a minus compared to a plus, so h of negative x does not equal negative h of x. So that one we would have found is not odd, it's not even, it's neither. Now, most functions are neither odd or even. It's really more of a special case for them to be odd or even. A couple of quick tips, though. If you have an odd exponent, it could be odd. If you have an even exponent, it could be even. If you have both, it is guaranteed to be neither. And then if we have an even plus even, two even functions, we get an even function. If we have an odd function plus an odd, we get an odd function. If we have an even plus an odd, we get neither, unless either of those functions is 0. But we don't really care about that. We also say odd plus a constant, such as like x cubed plus 1, is neither. But even plus a constant is even, because we can go up and down on the y-axis and be okay. So that would be like x squared plus 1. Otherwise, that's probably plenty to think about. And that'll kind of help you determine, but really you want to do these tests to be absolutely certain. Okay, so continuing on here, let's look at some graphs and determine the type of symmetry. So first one, I can see that this is odd. This is kind of the example I've been doing, x cubed. So we would say if we rotate 180, would map to ourselves. If we reflect and reflect again, we would map to ourselves, so it's definitely odd. This one is neither. I don't have symmetry over the y-axis. I don't have symmetry over the x-axis. I have this point not on the origin, so it's basically my same function just shifted over, so that doesn't do us any good. This is neither. I don't have symmetry over the y or the x or anything like that. I'm not on the origin. This is even symmetry, so we are symmetrical over the y-axis, but we are certainly not symmetrical over the x-axis, so no dice. This is neither. Function would have some decent symmetry, and if we were to shift this back to here, this could be considered an odd function, but we are not. We are shifted off of that. We do not go through the origin, so we're certainly not odd. We're not even, so we're neither. This looks like a logarithmic function. Log is neither. I can't reflect over the y and have the same thing. I can't reflect over the x. I can't rotate. This looks nice and even. We have symmetry over this y, so if I reflected, I would end up right back on myself. This is neither. We do have symmetry over some axis of symmetry, but it is not the y-axis. This is where we're supposed to have the symmetry over to be considered even. Last one's pretty tricky. We go through the origin, so that's a candidate, so maybe it's odd. And if you kind of imagine, like if I reflected this over the y-axis, that would look something like this. If I reflect it again over the x-axis, or if I did that, I would look the same. So this is odd, or I could imagine rotating 180 degrees. Even though it's a little tricky to imagine, we do map onto ourselves. So we are, in fact, an odd function. Okay. Now we have some algebra to work with. So we want to determine the symmetry of the function. If it's even or odd, prove the symmetry. So right off the bat here, imagine the graph. You can kind of just say it. We're only a candidate for even by this power, but because we are shifted on our vertex somewhere over here, it's going to be neither. However, we're supposed to prove that, so I want to see, does f of x equal f of negative x? Okay, now I'll write that right here. Even, we said f of x is f of negative x. That was messy. And we said odd, negative f of x equals f of negative x. And then you can kind of narrow down. So we said this one is neither, but just to confirm like that it's not even, we're going to do f of negative x equals negative x plus 3 squared minus 1. Square of a binomial, we would get x squared minus 6x plus 9 minus 1, or x squared minus 6x plus 8. If we were to expand this initial one, we would have gotten x squared plus 6x plus 9 minus 1, x squared plus 6x plus 8. So they are not the same. F of x does not equal f of negative x. From our rules before, we said we can't add odd and even, or odd and a constant and still be odd. So this is just going to be neither. If you wanted to test them, you could. You could plug in f of x, or g of x, I guess in this case. So g of negative x is going to give us negative x cubed plus negative x squared plus 1, which is going to be negative x cubed plus x squared plus 1. So already that's failing the even test, so not even, because g of x did not equal g of negative x. Then we can try our other one, odd, so negative g of x is equal to negative x cubed plus x squared plus 1. Negative g of x equals negative x cubed minus x squared minus 1. But that is not the same as this, so it's also not odd. Okay, with h of x, we are a candidate for being odd. We have this odd power. We don't have any even powers. We said odd plus odd plus odd is supposed to give us odd, so I already know this is an odd function. However, why don't we just confirm it, because it's good practice. So h of negative x is going to be negative x to the 5th plus negative x cubed plus negative x, aka negative x to the 5th minus x cubed minus x. Okay, compared to, do a little brown, negative h of x equals negative x to the 5th plus x cubed plus x. Negative h of x equals negative x to the 5th minus x cubed minus x. These are the same, so it is odd. So we would say h of negative x does equal negative h of x. Our next one, it looks like we are looking even. We have x squared over, or x to the 4th plus x squared all over 5. That really is sort of even plus even, and then the divided by 5 is just scaling us down, so that's not really a problem. Let's circle some answers. So this is definitely going to be even. However, we ought to confirm that, so let's go in red. We'll say j of negative x equals negative x to the 4th plus negative x squared over 5. j of negative x equals, well, that's the same thing as x to the fourth plus x squared over 5 equals j of x. So j of negative x equals j of x, and we are happy. F of x, this one's not so obvious. There's no even powers here, so it's certainly not even. So it's not even because we don't have anything even that looks like it's happening. We also don't go through 0, 0. As far as I can tell, I mean, I plug in 0 for x and I get negative 1/2, right? So that's not going to be odd. Based on that, we're going to say neither. Again, let's do the practice though. So f of negative x is going to equal 3 times negative x plus 1 all over negative x minus 2. F of negative x equals negative 3x plus 1 over negative x minus 2. So that's not the same as the first function. Can't really factor out any negatives and make them look the same. So that's no good. Not even. Right. Let's check negative f of x, which would be equal to negative 3x plus 1 all over x minus 2. No matter where you apply that negative, it's not going to match everything else. We're going to get negative 3x minus 1 all over x minus 2 if we distribute it to the numerator. And that's just, I mean, it's not odd, it's not even, doesn't really match anything. Okay, next one is a quadratic x squared minus 2x plus 1. That one probably going to be neither, right? We have even plus odd. So that's going to give us neither. Also, that's a square or perfect square trinomial, so we could factor this to be x minus 1 squared, which represents a shift off the axis, right? So here we are, and here's our axis, and here's our axis, and we're hanging out somewhere there, so it's not symmetrical over the y-axis. Our symmetry is sort of out here. But again, I mean, we could test it. Yeah, whatever. Algebra practice never hurts. So let's go green. So h of negative x equals negative x squared minus 2 negative x plus 1. H of negative x equals x squared plus 2x plus 1. Okay, so that's not the same as original. It's not even. Negative h of x is going to equal negative x squared minus 2x plus 1. Negative h of x equals negative x squared plus 2x minus 1. So our original h of x are h of negative x. Green was a poor choice. Our original h of x are h of negative x and negative h of x. None of that actually matches. So it's nothing. It's neither. So that's going to summarize even and odd functions. You saw some examples on graphs, how we'd look at some equations for it. Yeah, that's how they're defined, and they have some useful applications. But yeah, awesome. If you have questions, please let me know or talk to your teacher.